Hello everyone and welcome back to this channel. Today's topic is designing of Iir filters. It is related to the subject digital signal processing for third year ENTC students. In the today's video, I'll be teaching you the major important methods which are used for designing of Iir filters. One is impulse invariance method, second is bilinear transformation method. Along with that, we'll be also discussing the mapping from Laplace domain to Z domain, which is again required for designing of Iir filters, and we will be discussing the concept of frequency warping. Now, first part is impulse invariance method. This is one of the methods which is used to design Iir filters. IIR stands for infinite impulse response. So first is impulse invariance method. What we are supposed to do in this method? Already someone has designed analog filter. That means equation of H of S is available. Note that S is the notation used in Laplace transformation. So all analog filters are designed using Laplace transformation. As I mentioned, someone has designed analog filter means H of S is available. H of S is transfer function of the designed filter in Laplace domain. That is definitely for analog filters. Then I have written the flow of sequence. So before that, if H of S is available, what is our target? We need to design the filter in digital domain. That means theoretically we need to obtain equation of H of Z. So derivation means convert H of S into H of Z. So these are the steps how we will be performing the derivation. We have the available equation of H of S. Take inverse Laplace so that you will get H of T. Then perform sampling, you will get H of N. H of N stands for discrete signal. Then take Z transformation, you will get H of Z. After performing this thing, we'll arrive at one particular formula which will be used to design Iir filter using impulse invariance method. Now, as I mentioned, all analog filters are designed in Laplace domain. So we have the equation of H of S. Let us say it is in the form k is equals to 1 to n ak upon s minus pk. This is the summation which represents there are n number of terms a1, a2, a3. I have written in terms of notation. So ak is the coefficient or constant simply. S minus pk. This term pk indicates poles of analog filter p1, p2, p3 and so on. So it indicates poles of analog filter. Now look at the flow. From H of S we have to obtain H of T. H of T is inverse Laplace transform. You don't have to mug up the tough formula of inverse Laplace. We need only one formula. If the equation is 1 upon S minus Pk, P1, P2, P3, whatever, its inverse Laplace is e raised to Pk into T. So if I will take inverse Laplace of this equation, inverse Laplace of H of S is H of T. Small notation is used, H of T. Summation remains as it is, k is equals to 1 to n. Ak is constant, it remains as it is. For this term, 1 upon s minus pk, I am using this formula. So it is e raised to pk into t. So this is equation of H of T. Now next step is obtain H of N by performing sampling. In case of sampling, theoretically, what you are supposed to do, if we have notation t, t is representing time period or it is in time domain. So replace t by n into ts. N represents discrete signal. Ts represents sampling time, which is 1 by fs, reciprocal of sampling frequency. So after this, I will be getting equation of H of N simply by putting t is equals to n into ts. So equation becomes summation k is equals to 1 to n ak e raised to pk remains as it is. In place of t, I am putting nts. So it is nts. So we will give some equation numbers. Say equation 1. This is say equation 2. Now look at the flow. From H of N, we have to obtain H of Z. Now the basic definition of Z transformation is H of Z is summation n is equals to 0 to infinity H of n Z raised to minus n. So this is the definition of Z transformation. H of n means this entire term I need to put in place of H of n. So equation of H of Z can be written as summation n 0 to infinity. This summation I am keeping as it is. H of n means this entire term I need to put it as it is. So this term is summation k is equals to 1 to n ak e raised to pk into n ts. I have kept this term as it is in place of h of n into z raised to minus n. This term will remain as it is into z raised to minus n. So simply rearrange the equations. I will rearrange it like this: summation k is equals to 1 to n. This summation along with ak, I am taking it outside. Remaining terms I will write it like this: summation n 0 to infinity e raised to pk n ts into z raised to minus n. So I have simply rearranged the equation. From these two terms, take n common. So this term, first summation, I will write it like this: k is equals to 1 to n ak. Second summation, summation n 0 to infinity. I will take n common from this, so it becomes e raised to pk ts into z raised to minus 1 bracket raised to n. So simply I have combined this equation, so it becomes bracket raised to n. Now we need to make use of one identity, a mathematical identity. See, if we have the equation summation n 0 to infinity a raised to n, its answer is 1 upon 1 minus a. So this is the formula which I need to implement over here. So this bracket term represents value of a. So the same equation can be written as h of z is equals to summation k is equals to 1 to n ak. This part I am keeping it as it is. In place of this second summation, I am using this formula. Answer is 1 upon 1 minus a. So it becomes 1 upon 1 minus e raised to pk ts into z raised to minus 1. So in very much simplified format, this can be written as summation k is equals to 1 to n ak upon 1 minus e raised to pk ts into z raised to minus 1. So this is say equation number 2. If you compare equation number 3, if you compare equation 1 and equation 3, equation 3 is the equation of h of z. That means it is the designing equation in z domain using z transformation. Equation 1 is in Laplace domain, that is designing equation for analog filter. So if you compare these two equations, what's the difference? In place of this s minus pk, we are getting this term 1 upon 1 minus e raised to pk ts into z raised to minus 1. So the conclusion is, if you want to transfer analog filter into a digital filter, then make use of the formula for transformation 1 upon s minus pk. See, this summation and ak is common in both the things, so I am not considering it. 1 upon s minus pk, if you transform to the value 1 upon 1 minus e raised to pk ts into z raised to minus 1, then analog filters can be converted into digital filters. So this is the formula which is used in case of impulse invariance method. The next part is mapping between S and Z plane. S is the Laplace domain which is used for designing of analog filters. Z is the Z domain used for designing of digital filters. The derivation starts with the equation Z is equals to e raised to pk ts. Just now we discussed poles of digital filters are located at this value. Z is equals to e raised to pk ts. Ts is the sampling time. Say equation number 1. Now poles of analog filters are located at S is equals to Pk. So in this case, in place of Pk, put the value S. So equation becomes Z is equals to E raised to S into Ts. S is the Laplace operator. Say equation number 2. Now the Laplace operator S is given as sigma plus j omega. Sigma is known as attenuation constant. This notation omega, which is also read as ohm, is analog frequency. This is the basic definition of Laplace operator S. Say equation number 3. Now similar to this, the Z operator, rather notation Z, is represented as R e raised to j omega. R is the value which is used to represent the ROC in case of Z transformation. R is also known as the magnitude of Z transformation. Omega is digital frequency. Now if you put equations 3 and 4, that means we'll put value of Z and S in equation 2. I can write R e raised to j omega is equals to E raised to sigma plus j omega into Ts. What I did, put the value of S and put the value of Z in equation 2. I got this equation. So if I will further simplify it, I will get R e raised to j omega is E raised to sigma Ts into E raised to j ohm Ts. Now we will equate real parts and imaginary parts. Imaginary part is the part which is containing notation J. So these two terms, this term and this term, indicates imaginary part, whereas remaining is real part. So if I will equate real parts, then I can write the equation R is equals to E raised to sigma Ts. Say this is equation number 5. And from this, if I will compare these imaginary terms, then I can write the equation as omega is equals to ohm or omega Ts. This equation number 6 gives the relationship between analog frequency and digital frequency. Now, mapping means we need to show graphically how the things are transferred from Laplace domain into Z domain. Mapping is related to equation number 5. Now, how to do the mapping? Before this, if you want to draw the diagram, then in case of S domain, the diagram will be like this. On x-axis, I need to plot sigma. On y-axis, I need to plot j omega. This is the diagram. This is also called S domain or Laplace domain. In case of Z domain, the diagram is like this. On this axis, I am supposed to write R. On another axis, I am supposed to write j omega. And in case of Z domain, always and always we need to draw a circle of radius 1. This is the circle of radius 1. So it is also called unit circle. This is the basic way how the Laplace domain and Z domain diagrams are drawn. Now, coming back to equation 5, mapping or transformation is related to equation 5. We'll consider different conditions. First condition, if sigma is less than 0. Look at this equation number 5. If sigma is less than 0, that means sigma is negative. Ts is sampling time having some fixed value. So e raised to minus anything is always between 0 to 1. So this gives R, value of R between 0 to 1. This is first condition. Second condition, if I will put sigma equals to 0, then again from this equation, if sigma is 0, 0 into Ts is 0, so you will get e raised to 0. E raised to 0 is 1. So this gives me value of R equals to 1. Third condition, if sigma greater than 0, then you are getting some positive, e raised to some positive term. So this gives R greater than 1. Now how to draw it diagrammatically? Sigma less than 0 means left hand side part of this diagram, because sigma less than 0 is negative value of sigma. This is the origin. So negative value of sigma means this portion. Actually this portion is still minus infinity, but as a convention I am drawing the rectangle and I am showing the shading like this. this portion represents sigma less than 0 in Laplace domain. Corresponding value of r for this is 0 to 1. 0 to 1 is which portion? This is the circle of radius 1. So 0 to 1 is the portion which is inside the unit circle. So we can say that left hand side part of S plane Laplace domain gets transformed or gets mapped inside the unit circle. Unit circle is circle of radius 1. This is one mapping condition. Second, if sigma is 0 is which portion of this diagram? See, on entire j omega axis, I mean to say, everywhere sigma is 0. So this red colored line indicates the position of sigma equals to 0. For this, what value of r I am getting? R is equals to 1 according to equation 5. R equals to 1 is the periphery of unit circle. That is this portion, periphery of unit circle. So we can say that entire j ohm axis is mapped on the periphery of unit circle. Periphery of unit circle is basically 2 pi r. So r is 1, so it is 2 pi. That means we can say entire j ohm axis, that means from minus infinity to plus infinity. So in simplified language, infinity values are getting converted into 2 pi number of values. So this is the mapping which indicates many to 1. Many things are equivalent to 1. It produces aliasing effect. This is the major drawback of impulse invariance method. Now, the third condition of mapping is if sigma greater than 0. Sigma greater than 0 means positive value of sigma. So positive value of sigma means at the RHS side. So here till infinity actually I am getting everywhere sigma greater than 0. So I am drawing it like this. This portion, as I mentioned, this is the value up to infinity, but as a convention I am drawing it like this. So this indicates sigma greater than 0. For this, r is greater than 1. R greater than 1 means which portion? It is outside this unit circle. Actually it is outside this unit circle till infinity. Again, as a convention, I will draw one rectangle and show the shading inside the rectangle. Ideally this portion is outside the unit circle and till infinity, but as a convention I am showing it like this. So RHS part of S plane gets mapped outside the unit circle. So this diagram represents mapping or transformation from S plane to Z plane. The second method which is used for designing of Iir filters is BLT, that is bilinear transformation. In this method, this is the formula which is used for transformation, that is S Laplace operator is replaced by 2 by Ts z minus 1 upon z plus 1. Now in BLT, in bilinear transformation, the relationship between omega or ohm, that is analog frequency, and digital frequency of this omega is given by equation number 1. Actually, we are deriving the equation for frequency warping concept which is there in case of the method BLT. So the derivation starts with equation 1. This is the relationship between analog and digital frequencies. Now, if we do this calculation on unit circle, then on unit circle value of r is 1. So in equation 1, for unit circle, everywhere for r I am putting value equals to 1. So it becomes 2 by Ts into 2 sine omega upon, in place of r I am putting 1. So 1 square is 1 plus 2 cos omega plus 1. So this equation simply becomes 2 by Ts into 2 sine omega upon 2 plus 2 cos omega. I have added this 2, 1 plus 1, so it becomes 2. Now in the second term, this 2 gets cancelled, so it can be simply written as 2 by Ts into sine omega upon 1 plus cos omega. Now for this term, we need to use the trigonometric identities which I have already written. Sine omega is 2 sine omega by 2 into cos omega by 2, and 1 plus cos omega is 2 cos square omega by 2. So let us make use of this identity. So it can be written as ohm is equals to 2 by Ts into, in place of sine omega I am putting this value, 2 sine omega by 2 into cos omega by 2 upon 1 plus cos omega is 2 cos square omega by 2. So it is 2 cos square omega by 2. Let us simplify this equation. This 2 again gets cancelled. Cos omega by 2 and this is cos square. So one term of cos omega by 2 gets cancelled. So simply you can write this equation as ohm is equals to 2 by Ts into this sine upon cos is tan omega by 2. Let us further rearrange this equation. So it can be written as tan omega by 2 is equals to, I will transfer Ts over here, so it becomes ohm Ts by 2. Therefore, omega by 2 is equals to tan inverse ohm Ts upon 2. What I did, I have transferred this tan term at the RHS, so it becomes tan inverse. Now, the next part is, I want equation of omega. Omega is the frequency used to represent digital signal. So I will simply get omega is equals to 2 tan inverse of ohm Ts upon 2. Note that Ts is the sampling time, which is some fixed value. Now for this I need to draw the diagram which is representing ohm Ts on x-axis and omega on y-axis. So if you go on putting different values of ohm Ts and if you calculate value of omega from this equation, then the graph will be like this. At the upper side this value is pi by 2, at the lower side it is minus pi by 2, and the graph is like this. Now if I will mark some points, say this point is A, this point is B. From A to B the graph is linear, so the name is BLT, bilinear transformation. Ideally it should be linear. So from A to B, since the graph is linear, it is both sided bilinear transformation. But the thing is that the equation contains 2 tan inverse term. Due to this 2 tan inverse term, graph cannot exceed beyond plus pi by 2 and minus pi by 2. Because the value of 2 tan inverse is pi by 2 and minus pi by 2 on both sides, max value. So the graph is not increasing beyond this value. This particular concept is known as frequency warping concept, which is existing in case of the method BLT. But the drawback of impulse invariance method, which was transformation was many to one, is avoided in case of BLT method. So dear students, that's it for today's video. I have explained you the important derivations or rather techniques used for designing of IR filter. Thanks for watching this video. Thank you very much.